Hi, thank you for your interest in my talk. My name is Prokosch, and I would like to show you some work that I've done together with François on a unification algorithm in a runtime environment. First of all, I would like to motivate our need for a new unification algorithm. We are currently implementing a first-order meta-level reasoning system. In this reasoning system, we want to have a unification algorithm which does not only give the answer unifiable or not unifiable, but returns more detailed information on the two expressions at hand. Given two expressions E1 and E2, we want to know whether expression E1 is strictly more general than E2. For example, f of V1, V2 is strictly more general than f of V3 and B. But we also want to know if expression E1 is a strict instance of expression E2. Then we want to return the matcher and the fact that E1 is a strict instance of E2. An example would be the expression f of A and B, which is a strict instance of the expression f of V1 and V2. We also want to know if expression E1 is a variant of E2. Then we want to return a renaming substitution and the fact that both expressions are variants. If expressions are unifiable but none of the three cases above, we denote this as expression E1 is only unifiable with expression E2. We want to return the unifier and the fact that they're only unifiable. An example for this would be the expression f of A V1 and f of V2B. They're only unifiable because V1 can be mapped to B and V2 can be mapped to A. And last but not least, of course, we also want to know when two expressions E1 and E2 are not unifiable. Then we would simply return not unifiable. Ideally, these results would be returned to us in a single run over the expressions E1 and E2. But then we also want to use low-level data structures for efficiency reasons. We only care about syntactic unification. And one thing to note as well is the term expression. Because our system should allow meta-reasoning, we do not want to make a distinction between terms and atoms, but we want to refer to those as expressions. So an expression constructor is either a function symbol or a predicate symbol. Now I would like to show you the low-level representation. I will start with the representation for expressions. In my examples, I will assume a word size of 4 bytes. First, I would like to represent this expression f of A V1 B V2 in memory. This expression consists of expression constructors and variables. In our representation, we require flags to be able to distinguish between those two types. Here in this representation, you see we have the word cons for constructors and the word var for variables. So when we put the first expression constructor f into the memory cell 0, then we prefix it with an appropriate flag. We also make sure to include the arity of the expression constructor because this arity is required later to know where the expression ends. Then we put the expression constructor A into the next memory cell, followed by variable V1. The variable is marked with an appropriate flag, but we do not store the variable name V1 since this name is not really relevant for uniquely representing an expression. Each variable has a unique memory address which we can use to retrieve the contents of the variable, which is nil if the variable is unbound. Similarly, we add expression constructors B0 and the variable V2 to the memory cells. We can see that the variables V1 and V2 are actually different variables because they are represented by different memory cells. In this example here by memory cell 9, or actually 8 to 11 and 16 to 19. In future schematic representations, I will omit the flags. We have seen in this example one kind of variables. I would like to denote them as non-offset variables. And one thing that we can observe is that non-offset variables only allow for representing linear expressions. Linear expressions are expressions where each variable occurs only once. But if we want to be able to represent nonlinear expressions, then we need to consider a new type of variables, which I would like to call offset variables. With these offset variables, we can, for example, represent the expression f of a v1 bv1, where the variable v occurs twice. The first occurrence is a non-offset variable, just like before, but the second occurrence at address 16 is a non-offset variable. The offset variable stores an offset, hence its name, which is used to refer to the corresponding non-offset variable. In this example, the offset is 8. We need to subtract this offset 8 from the first memory cell the variable belongs to, which is 16, and this yields the memory address 8, where the base variable of the offset variable is located. Now that we have seen how expressions and variables can be represented in memory, let us turn towards substitutions. Substitutions are conceptually very simple because they are basically tuples of variable and expression addresses. When we want to apply a substitution to an expression, we simply replace the nil value of the variable in the expression with the memory address of the expression to be substituted. For example, let us look at the substitution here written with v1 maps to q, b, v3, and in an in-memory representation it would be represented as the tuple 8 and 24, because variable v1 is located at memory address 8, and the expression to be substituted starts at memory address 24. We only have to change a single value in the expression to which we apply the substitution. In this case, it is the variable located at address 8. It is changed from the nil value to the value 24, so the target of the substitution. Please observe that we have the variable v1 twice in the expression, once as a base variable at address 8 and once as an offset variable starting at address 12. And only the base variables are substituted. The offset variables stay unmodified. The fact that offset variables stay the same does not really matter, because when they're dereferenced, they first point towards the base variable, and the base variable now has the correct binding. Now that we have seen expressions, variable, and substitutions, we can look at the matching unification algorithm. The matching unification algorithm works by traversing two expressions concurrently from left to right, thereby comparing the memory cells of each expression based on type and content. To be able to perform these comparisons, we need a couple of functions. The first function that we are going to look at is the function type, which yields either cons, nowar, or offvar, depending on the flag of the memory cell, which can be found at address E. Of course, we also need to get the value of a memory cell, and we also need to be able to get the arity of an expression constructor. If E points to a memory cell which does not contain a constructor but a variable, then we simply return the arity 0. Then we also need a dereferencing function which takes an expression representation located at memory cell E and a substitution, capital S, yielding a new expression as the result where the substitution has been applied to the expression. And finally, we require an occurs check, which simply checks whether the variable located at cell E1 is contained in the expression that is represented by memory cell E2 and following. When we unify two expressions which start at addresses E1 and E2, we need to distinguish 4 cases. The first case is when we encounter a constructor. The second case is when we encounter a non-offset variable. The third case is we encounter an offset variable, which is non-nil when dereferenced, so it is a bound offset variable. And the fourth case is when we encounter a non-bound offset variable. That is an offset variable whose base variable is still available for binding. Because of those 4 cases can occur with both expressions, E1 and E2, we have to consider a total of 16 combinations for the unification algorithm. However, some of the cases are similar. For example, it really does not matter whether we encounter a constructor in memory cell E1 and a non-offset variable in memory cell E2, or whether it is the other way around. In this case, we can simply use the same approach for unifying E1 and E2, but we need to swap variables E1 and E2. This is helped by the fact that the matching and unification modes variant, only unifiable and non-unifiable are symmetric, and that the strict instance is the exact opposite of a strict generalization. So when expression E1 is a strict instance of expression E2, then the expression E2 is a strict generalization of the expression E1. Due to this, the 16 cases can be arranged in a square table which is almost symmetric along its diagonal. However, this symmetry is unfortunately not a perfect one. The main reason being the following situation. When we need to unify 2 non-offset variables, we know that these variables occur for the first time and they cannot have a binding. But we do have to create the binding now, and we have 2 possibilities for this. We can either bind E1 to E2, or we can bind E2 to E1. Both cases are completely equivalent and we can choose either of them, but we must not bind in both directions because this would introduce a circular dependency, and this is not a possible solution. We chose in our algorithm to use the latter binding, so we bind to the left, which means that we bind variable E2 to the expression located at E1, and variable E1 remains unbound. So let us review the algorithm very briefly. The details can be found in the article. We traverse the expressions left to right, and each pair of memory cells encountered during the traversal is compared by type and by value. First of all, if we encounter 2 expression constructors, then we need to check whether these expression constructors are equal. If they are, then we continue comparing, and in the other case we return the result that these expressions are not unifiable. If we encounter an expression constructor and a non-offset variable, then we can bind the non-offset variable to the expression constructor. You also must make sure to change the mode if necessary. So a variant may need to be changed into a strict instance or a strict generalization, and a strict instance or a strict generalization may need to be changed into only unifiable. If we encounter an expression constructor and an offset variable which is already bound, so not equal nil, then we perform a recursive call in order to check whether these two expressions are compatible. And finally, if we encounter an expression constructor and an offset variable which is still available for binding, then we need to perform an occurs check, because we need to ensure that the base variable of the offset variable does not occur in the expression denoted by the expression constructor. And after that, we may either bind the offset variable and return only unifiable, or if the occurs check says that the variable occurs in the expression, then we must return non-unifiable as the unification mode. The case with the non-offset variable and the constructor is actually symmetric to the case above, where we had the constructor and the non-offset variable. So this is why I have put an empty cell here in the table. Then we already discussed the case where we have two non-offset variables. Here we bind to the left. And if we observe a non-offset variable and an offset variable which is already bound, then we bind the non-offset variable to the binding and eventually change the mode. And if we encounter both a non-offset variable and an offset variable which is unbound, then we can bind the non-offset variable to the offset variable, and we also may need to change the mode. Then if we encounter two already bound offset variables, then we need to make sure that the bindings are compatible. We do this in a recursive call on the dereferenced expressions. And if we encounter both a bound and an unbound offset variable, then we try to bind the unbound offset variable to the expression referred to by the bound offset variable after we performed an occurs check. And finally, the last part in the table, if we encounter two bound offset variables, then we can bind their base variables to the left. An example should illustrate how this matching unification algorithm works in practice. Let us assume that we want to unify those two expressions f of v1, v1 and f of a and a. The low-level representation of the first expression is f2 nil 4. The second representation is f2 a0 a0. We start by comparing the memory cells 0 and 20. We see though that those memory cells contains expression constructors and their values match. So we need to read two more memory cells because of the arity of the expression constructors is 2. We make a note to read two more memory cells and continue. We continue with the next memory cell containing a non-offset variable in one expression and an expression constructor in the second expression. This allows us to bind the variable to the expression denoted by the expression constructor. So we add to the substitution S1 the tuple 4 and 24, 4 being the variable address and 24 being the address of the expression constructor. Then we continue traversing and we encountered memory address 8, the offset variable with the offset 4, which refers us to the variable at address 4. We know from the previous step that this variable is bound to address 24, corresponding to the expression A0. The second expression is at address 28, and so in a recursive call we compare addresses 24 and 28. We find two expression constructors, and we see that these expression constructors have the same value and they are equal, so we can simply return variant as a result of the recursive call. Then we would try to read more memory cells, but actually our expressions are done. So there are no more memory cells to read, and we can return the result, which is still variant. And this is also the correct result. Finally, I would like to say a few words about complexity. The complexity of the algorithm is determined by several factors. First of all, the number of time steps for traversing the expressions is bound by the length of the expressions. The maximum of those values is an upper bound for the time required for the traversal. The number of time steps for traversing the expressions need to be multiplied by the number of how often sub-expressions may need to be revisited. The number of revisits depends on the number of offset variables, because non-offset variables are always bound without looking at sub-expressions, so they're kind of skipped. Bound offset variables, however, require a compatibility check and as a result also traversal of its binding. The third consideration is that the occurs check requires an unbound offset variable. The number of occurs checks is limited by the number of offset and non-offset variables, since we need at least one of each type. So the number of occurs checks is strictly smaller than the length of the expression. With these explanations, we can now understand the formula of the complexity of the algorithm, which is in the order of the maximum of length of E1 and length of E2 multiplied by the maximum of 1 and the number of offset variables in E1 added to the number of offset variables in E2. To conclude, I would like to stress that the flat representation is sufficient for an efficient unification algorithm. The complex data structures that occur in many unification algorithms are not really necessary in our opinion. Then, one of our most interesting findings is that the distinction between non-offset and offset variables can greatly reduce the number of necessary occurs checks. And finally, the matching and unification modes can be determined during the unification algorithm, which is way faster than doing this in a separate step after the unification. Thank you for your attention.